The people that bring the scooter back. They put them back to
Excuse me.
It was not an
I will begin. Let me see how late I'm starting. So I know, oh man, I'm starting 5 minutes late. That means I need to go 5 minutes over. All right, I will begin. Heavenly Father, we thank you for this day. I thank you for these students. And just ask you to just guide our steps today. Help us to understand more about Cauchy's integral theorem and its consequences, and just how to calculate all these things. Lord, in your name I pray, Lord Jesus. Amen. Okay, so basically last time we proved a pretty cool formula, and it is this. The integral, the nth derivative of a function, holomorphic function, f of z at z naught is equal to m factorial divided by 2 pi I times the integral. Well, we proved it for a in a more general context, but at the moment I'm going to look at it for a disk, a closed disk, z minus z naught less than or equal to rho. And so we proved a more general result last time, but I'm specializing here for the moment. All right, so the thing we proved generally last time was we didn't have to have just a disk there. What did we have? What was the context we did last time? So last time, the context that we had was that if we had a function f that was like, so your region could have been like this. It could add holes. It doesn't really matter. But suppose that, inside this region, so we had what f was holomorphic on this region, what do you want to call it, R, on and near R. And then if z naught is just some point, and I think the z naught doesn't have to be, oh goodness, I'm trying to remember. Let me not butcher the statement of this. We had it so nicely stated last time. Let D be a bounded domain, piecewise smooth boundary partial D, f of z holomorphic and continuous on D. Right, then for each z in D. So the z had to be in D. So like z naught would be in here, for example. And instead of this, we had replaced this with like the boundary of R. All right, or I guess it was D. So that was the theorem we proved last time. This is Cauchy's generalized integral formula. But instead of looking at that, I'm just looking at, what? I'm looking at simply, z naught. And, well, this is nothing more than the disk of radius rho, right? So if I apply Cauchy's generalized integral formula to a function f, which is holomorphic on this disk and near it, then we have this formula, all right? But we can do more, right? Because we can parameterize the circle, right? And we can actually sort of do this calculation. In particular, if we have, how would we parameterize the circle? What would we give here? Okay, you said, say we'd have f of z naught plus rho e to the it, right? Divided by what? Rho e to the it to the m plus 1 power, right? And then my dz is what? My dz is I rho e to the it dt, right? And we're integrating from 0 to 2 pi, right? So that would be the formula in practice. And what that works out to, right, is actually what? M factorial divided by 2 pi rho to the power what? Rho to the power m times the integral from 0 to 2 pi f of z naught plus rho e to the it times e to the what? What does that simplify to? If you look at all the imaginary exponentials you got there, you're just left with one m in the denominator, which we can bring upstairs, e to the minus im t. I guess I'm using theta in the notes, but I'm using t on the board. Hope you can forgive me. T is equal to theta. So from this calculation, right, which is just a straight application of Cauchy's integral formula, right? Nothing really snazzy here at all. What do we have? If f of z, right, is less than or equal to m on this this disk, right? Well, not even the disk, but just wait. Hold on a second. That's not less than or equals to. That's nonsense. Can you integrate? Is the complex integral over an area? No. What's that supposed to be? That's equals. Thank you. So if this is true on the circle, I do need that f is holomorphic on the disk in order to apply the formula, right? But if f is bounded like that, then what do you see about the mth derivative? What's the bound of the mth derivative at z naught? So it's less than or equal to m factorial divided by 2 pi rho to the power m times, the absolute value of this integral. But what is this integral actually? Can you tell me how the integral would be bounded then? So this whole integral, if we're given that the modulus of f is at most m, then this integral is bounded above by just 2 pi m, right? Because like the e to the imt doesn't do anything. That was a minus, my bad. Anyway, what we got here? So this means that the mth derivative at z naught is less than or equal to m factorial times big M divided by rho to the power m. If I haven't missed something. So this right here has a name, and as most things, as are most things in this course, we're going to name it after who? Cauchy. Very good. So this is Cauchy's. Good. That's a good guess. But this is in fact Cauchy's estimate. So Cauchy's estimate is just a natural consequence of applying Cauchy's integral formula to a function, a holomorphic function on a disk. Again, the context here is that if, just the preamble here, the boxed formula holds true when we need f, holomorphic on the disk z minus z naught less than or equal to rho, then we get Cauchy's estimate, namely that the mth derivative at z naught, all right, modulus of that is less than or equal to m factorial times m. Now, if you notice carefully here, I've just introduced yet another concept, which is holomorphic on a closed set. What do we mean by holomorphic on a closed set? What's that going to mean? We've been dancing around this idea like last class even. I kept talking about functions being holomorphic on a region and then extending continuously to the boundary of the region, right? Well, that idea is that there's a little bit larger set on which it's holomorphic. So like, here's the picture. Here's the radius rho disk centered at z naught. Okay, so there's like a little bit bigger a little bit bigger disk, right? Which we could call, say, U, and F is an element of the holomorphic functions on U, right? So that's the idea here. So this is called Cauchy's estimate, and it straightaway leads to a result which is known as Liouville's theorem. So what's Liouville's theorem? I always forget how to spell this. Don't worry, he's dead. Liouville's theorem. And here it is. Suppose f of z is holomorphic. All right, with continuous derivative. You know, f prime of z. On C. All right, period. If f is bounded, if the modulus of f of z is less than or equal to m, then f of z is constant. In other words, Liouville's theorem says that the only bounded entire functions on the complex plane are nothing more or less than the constant functions on the complex plane. Now the proof of this is actually one of the more fun proofs to do in here, because it really just is a natural outgrowth of the Cauchy estimate. All right, so suppose that you have f holomorphic and continuous with derivative, right, and it's bounded. What do we get then? So we apply, so assume this is the case. Let consider, let's say rho equals to r, just for the sake of changing the letter, because I don't like rho. Right? Then, modulus of f of z less than or equal to m. Then we can use z not equal to 0, right? So we'd have, well, excuse me, let me not do z not equal to 0. We could do, pick any z naught, right? I mean, consider this z naught a particular element of the complex plane, right? And what does this estimate tell you in the case m equals to 1? So we have f of z holomorphic, right, on modulus of z minus z naught less than or equal to r, right? Apply Cauchy's estimate with m equals to 1. What does it say? It says that the modulus of f prime of z1, f prime of z naught, right, is less than or equal to what? Big M over what?
R.
Over, but m is 1, right? So over r. R. But notice that we can make r as big as we want, right? Because we have that the function is holomorphic on the entire complex plane, right? So what does that mean? That means that the derivative at z naught can be made arbitrarily small, right? At every single stupid point, because z naught's totally arbitrary as well. So what does this imply? Exactly. This implies that f prime of z naught is equal to 0. And in fact, it implies that f prime of z is equal to 0 on the whole complex plane, which says what? F of z is equal to a constant. Right? That was a theorem we had. If the derivative's everywhere, if the derivative is 0 on a connected set, then it implies that the function's constant. Going back to the function we had even before we talked about complex differentiation, if the gradient of a function on the plane is 0 on a connected set, that forces the function to be constant. That's true for the real, it's true for the complex. So that's a very nice result, right? What can you do with it? Well, my current set of notes don't have much because I was not, what I have written past this point in my notes is too heavily invested in Gamelin, and I didn't want to take you guys down that path because it's just, I don't know, it's just not quite right for this class this semester. So I decided to use this book here for our purposes in the next 20 or so minutes. I'm not going to prove everything. I'm going to try to prove some things, but so let's look at the so this Liouville's theorem. We can then use this to prove the
I was just going to ask you a question. Would that imply that any holomorphic function that, well, obviously you said that any holomorphic function that's continuous has a continuous derivative on C. That means like that if it's holomorphic on all of C, then its derivative will always be constant, or will always be 0.
Let's see here. If the function is bounded, it follows, I think it follows its derivative is also bounded by some of these things we have written here. I mean, if we fix the context, right? Like if you're talking about with respect to some closed disk, let's say, and you know that the function is bounded on that closed disk, this estimate immediately tells you that the arbitrary derivative is also bounded on the closed disk. So it would then mean that, yeah, the derivative would also be constant, which is not surprising because if you have a constant function, right, then all of its derivatives are also constant. Like we could prove that with much less sophisticated machinery, you know, like we could have proved that like day 2 complex differentiation wise, but what's interesting today is towards the end of class, I will prove in fact that this is an unnecessary assumption, that if the function's holomorphic on a reasonable set, it's automatically the case that the derivative is continuous. It's impossible to have a holomorphic function without having a continuous derivative. Like this is inevitable. Okay. But let's get to more. I wanted to start class with more interesting things because the proof of what I just talked about is rather technical, and I'd just like to point and click with you guys because it's the proofs of Morera, the theorems of Morera and Goursat, which establish that what I just said. They're a little bit technical. I think it's good for you guys to see the proofs, but I also don't really want to require you to do the proofs on like time pressure test or anything. And I really want you to see them, but they don't, as far as I know, they don't lead to any kind of calculational technique. The things I'm sharing with you right now have hope of having like a computational application, and in fact they will. We'll see that here. So, well, it's hard to get more computational than this. This theorem. So I just posted this, guys, in Canvas, and so you might not have noticed yet, but I posted a scan of like a section from Saf and Snyder's book on complex analysis, and so I think their section on the boundedness of analytic functions, it's pretty readable, and it just has exactly what we want to talk about in here. So anyway, so this is their theorem 22, but you might recognize it. Every non-constant polynomial in, let's say, CZ. So this is a notation for the complex coefficient polynomials, has at least one zero. So do you guys know the more popular name for this theorem? Yeah, it's a fundamental theorem of algebra. Now, I was told by one of you, I forget who it was, I should remember. Was it you, Jack? Somebody told me that Sperano proved this in Algebra 2. That was you? Okay. Sorry, I should remember what you told me like an hour ago. It's ridiculous, but... So the proof here, you can either take a kind of... I like the direct proof, and I think what we're about to see is a direct proof. So let's look at it. A lot of the proofs of the fundamental theorem of algebra, there's some sort of proof by contradiction. Like I think in your homework, there will be a proof by contradiction based on Cauchy's integral formula. All right, there's another, there'll be at least 3 distinct proofs of fundamental theorem of algebra we'll look at this semester. This might be my favorite. No, that's not true. The proof at the end of the course is probably my favorite, but here goes. So suppose, let me get to it here. I don't want to hurry too much at the end. P of z is equal a sub n z to the n plus a sub n minus 1 z to the n minus 1 plus dot 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 plus a1z plus a sub 0. All right? With a sub n not equal to 0, okay? So we're going to suppose this, and we're going to suppose more. Suppose this has no zeros, right? It has no zeros. Let me demystify that. That means that there does not exist, let's say, C, right, in the complexes such that what? P of C is equal to 0, right? That's what we mean by 0, just to be clear. Okay? Right. So we might notice that we can write P of Z as, Zn times what? Zn times a sub n plus a sub n minus 1 over z plus dot 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 plus a1 over z to the n minus 1, right? Plus a sub 0 over z to the n. You guys see that? What did I do? I just factored out z to the n. Do you agree? I hope you can agree I can do this, right? And you should also agree that from this, apparently, if we look at P of z over z to the n, right, that will go to a sub n as the modulus of z goes to infinity. All right? And if that limit exists, it follows the modulus of P of z over z to the n. It's got to be greater than or equal to the modulus of a sub n over 2 for z sufficiently large. Let's say for modulus of z greater than or equal to rho for the sake of discussion. Now, that right there is a homework problem. That claim is a homework problem. All right? It's intuitively clear. Let me just run through it why it's intuitively clear. If this limit exists, right, that must mean that the thing that's being limited is bounded. Because if the thing that was being limited was unbounded, you can't very well settle in on a to the n, a sub n, right? And if that limit's going to a sub n, that means that the values of this quantity have to be getting close to a sub n, right? I'm talking about moduli here, okay? So the modulus of this has to be getting close to the modulus of a sub n eventually, which means past some point you have to be bigger than half the modulus of a sub n. So this is a reasonable estimate. But I think there's ways to make that more rigorous and precise, and there's like a homework problem from Churchill's complex variables that I have that I can share with you guys. And as with everything, I think it's geometric series to like make it rigorous. But hopefully I'm remembering things correctly here. Anyway, so once you have that, then you can do things that are pretty nice. Then check this out. For the modulus of f of z, right, is equal to 1 over modulus of p of z, all right, which is less than or equal to 2 over the modulus of z to the n times the modulus of a sub n, which is less than or equal to 2 over rho to the n modulus of a sub n, all right? And this, of course, is for modulus of z greater than or equal to rho. Yes?
Is A real or complex?
These are all complex. But notice I've taken the modulus here, so I'm able to write estimates. But this is, in fact, a complex limit. But I mean, I would argue, depending on how fussy you want to be, right? This, again, depending on how fussy you want to be, is either enough, you know, getting to here, like this is just, depending on which class you're teaching, this is either intuitively clear, all right, because you're teaching a computational math course and you don't delve into these details, or if you're a math major, there's something here to establish. I think it's intuitively clear, that claim, but it's by no means been shown with what I've written. Yeah.
Are we saying f of z is just 1 over p of z then? Is that how we're defining it?
Oh yeah, I should probably define that. Thank you. If f of z, thanks Ben, is equal to 1 over p of z. Sorry, I always get distracted by the thing that's hard to understand and forget about the obvious thing, which is that f of z is 1 over p of z. So looking at that, it's bounded, right? So you got, what's the story here? Here's your radius rho disk, right? And this is what? This is outside, right? Outside. This is an exterior annulus, right? That's case number 1. What else is there to consider? How do I know that f of z is less than or equal to m for modulus of z less than rho? Like, how do I know that this case, this in here, right? This hideous Carolina blue hatched region, how do I know that there's a bound there for the function? Like, we're assuming what? Well, it's a reciprocal of a polynomial. Is it continuous? Very good. It's continuous because we're assuming that it has no zeros, which means the one trouble for a reciprocal of a polynomial, namely division by 0, is not present here. Therefore, yes, it's continuous. Therefore, being that it's continuous on a compact domain, if you put equality here, it's compact, right? Then the extreme value theorem says that there's a maximum attained by the modulus here, right? So what do we have altogether? Put 1 and 2 together, what do you have? I don't think it's a contradiction. I don't think it's a contradiction. What we have from 1 and 2. Now, in Dr. Sprando's class, it'd be a contradiction because he's just very, you know, what's the word? Contrary. So from 1 and 2, you could sell it as a contradiction if you wanted to, but I'm going to sell it as a direct proof. From 1 and 2, we find that 1 over p of z is bounded on the entire complex plane. But 1 over p of z is also an element of the holomorphic functions on the complex plane, right? So it's an entire bounded function. Therefore what? It must be, by Liouville's theorem, it must be constant, right? So therefore 1 over p of z is equal to, let's say, you know, c, which then tells you that, you know, p of z times c is equal to 1, which through the magic of polynomial algebra tells you that your formula for p of z is exactly 1 over c. In other words, by direct polynomial algebra, a sub j is equal to 0 for all j equals to 1, 2, and so forth. and a sub 0 is nothing more than 1 over this constant, whatever it is. And that's the theorem. Well, I guess that's not quite the theorem yet, is it? It says that, okay, at the moment all we've proved is that if your polynomial has no zeros, it has to be a constant, right? So what does that then mean? If your polynomial is not a constant, it must have a what? It must have a 0. So you Math 200 people, tell me what that is. That must be some kind of is it contradiction or is it contrapositive? It's contrapositive, I think.
Which is the type of
I think it. Oh, that is a type of contradiction. See, this is why I need.
No, it is a contradiction though, because didn't we assume that it's not a constant?
No, I didn't assume it wasn't a constant. I just assumed that it had no zeros.
Yeah.
And I showed that if it has no zeros, it has to be constant. That's not a contradiction. That's just a construction. Listen, I don't care what you call it, whatever you want. You know, just call it whatever you want. But it is a logical argument nonetheless that proves the fundamental theorem of algebra.
The most concise way versus the least concise way?
Well, the most concise way to prove the fundamental theorem of algebra is simply to say the fundamental theorem of algebra is true because I'm a teacher and you must accept it by my authority. So that is the most efficient and common proof of the fundamental theorem of algebra that's offered across this land. Certainly a very popular proof. All right, so now I'm just going to tell you some theorems that are a little bit shocking and can be proved. So like typically past this point in the course, people prove the mean value property. So the mean value property, I'll let you guys prove that in the next homework. I'll walk you through it. I won't like just say prove the mean value property and just leave you out to your devices. I'll try to, I want to write up the problem that just kind of walks you through it. It's not hard. It's really just a calculation, really. And the thing is, well, the funny thing about the mean value theorem, mean value property for complex function, which I guess I should write down since I'm talking about it so much, right? But we use the mean value property, which is this. The mean value property was that f of z naught is equal to 1 over 2 pi integral 0 to 2 pi f of z naught plus r e to the it dt. So so here the story is we're talking about like a circle of radius r centered around z naught. And what this theorem is saying is that the value of, and of course the function is assumed to be what? Holomorphic on the disk, right? So it's saying that what this is, right, is essentially the average. It's the average of f on CR, right? So here this circle is CR for the sake of discussion. The mean value property says that the value of the complex function, the holomorphic function around the thing, is just equal to the value at the center. This is the mean value property. Now, I use this in a critical point in proving Cauchy's integral formula. So it should not come as any surprise to you that if you want to derive this from Cauchy's integral formula, it's like super easy, right? Because it's baked into the cake of Cauchy's integral formula. So of course you could prove this from Cauchy's integral formula because we used it to make it. But we'd like to have a proof of this that's independent of Cauchy's integral formula for the logical coherence of our course. So that's one thing. But once you have that, you can use this to prove that the following theorem: a function analytic, what's that mean? In a bounded domain. So analytic is just holomorphic, guys, okay? In a bounded domain. And continuous up to and including its boundary get this, attains its maximum modulus on the boundary. So this, of course, is shockingly called the maximum modulus theorem. I'll show you, let's take a look at their example of this, okay, just to appreciate what it's saying more. I really hope this example's not bad. So, example 1, he's like, find the maximum value of modulus z squared plus 3z minus 1 in disk modulus of z less. In other words, modulus of z less than or equal to 1. In other words, in the unit disk, all right? And so what he does is he's like, okay, so we can use the triangle inequality. What do we have here? Z squared plus 3z minus 1 modulus is less than or equal to modulus of z squared, right? Plus 3 times the modulus of z plus 1, right? That's the triangle inequality here. And then what can we do? Well, for modulus of z less than 1, that's less than what? Less than or equal to what? Whoa. What'd you say? 1 plus 3 plus 1, also known as 5. Yes. Let's see here. So let's see. Does the theorem apply? We've got what? A function analytic on a bounded domain, continuous including. Certainly this is polynomial. It definitely satisfies the terms and conditions here. So allegedly this attains the maximum modulus on the boundary. Supposedly it has to be less than 5. And so what they do is they just shove the parameterization into it, and the details aren't all in here, but I'll just kind of sketch them. Like Sappho doesn't have details here either. So we have e to the it, we could do that, right? And if you put that in, you get what? Modulus of z squared plus 3z minus 1 is modulus of e to the 2it plus 3 times e to the it minus 1, right? Which is what? Equal to, oh, it's a mess. How does he? Yeah. Okay. Lovely. So, well, aren't you Mr. Fancy Pants? Let's see here. Okay, so through magic not shown in this book either, this allegedly, oh, he squares it. He has the good sense to square this thing. And with that squared, after some calculation, that turns out to be 11 minus the cosine of 2t. Sure it is. Now that though, what if you believe that, and it's in a book, right? It had an editor. It must be true, right? Yeah. This is, by the way, Saff and Snyder is a very good book. If I was to use another book, it would almost certainly be that one. I dislike the use of the word analytic so early in the book. I think analytic should be attached to the concept of power series, and it bothers me when the book doesn't do that. That's why anyway. How big can this be? This you don't need calculus for. This you're a pre-calculus student, you can answer this question. Oof. Oh, cosine t, 1, okay.
I thought there was a modulus next to the 1, it's 11.
11.
11, okay. But how big can this be? 12, right.
Oh, because it goes to 9.
Yeah. What the what? Oh, okay. I was like, and it says, and then it says the maximum of it is actually the square root of 13. So that, no, it's very simple. It's that I've lost a very important thing. There is a 2 here. All right, so this is less than or equal to 13. That's just pre-calculus. And in fact, if you want to, you can try putting in I. If you put in I squared plus 3 times I minus 1, what does that give you? That gives you minus 2 plus 3i, right? If I didn't mess it up, which is debatable. And what's the modulus of that? 9 plus square root of 13, right? So that actually, z equals to I, right, is, oh, and where is that, by the way? Unit disk. Where did we find the maximum? Here? Or here, if we actually do all the calculations. So that illustrates the maximum modulus, that if you have, holomorphic function, then the maximum modulus must be attained on the boundary. Right, this is the maximum modulus theorem. All right, I need to wrap up this stuff here. So that alone I don't think is, I'm kind of always been like, oh, okay, fine, cool. But what happens next is that ends up having, that ends up meaning things about the existence of solutions to Laplace's equation. Let's see here. Well, you know what, I won't try to say anything about that because I don't have quite enough time to do it justice, but maybe we'll come back to that when the time is right. This is the main thing you need to be, it would be a disservice to you for me not to at least talk about this. I don't always test it too deeply because I personally don't have a deep intuition for it, and when I make problems up about this, bad things happen. So it's a worrisome topic for me personally. I have a much deeper understanding of other things in this course. Anyway, who cares what I understand? All right, let's see here. Well, I hope you care a little bit. You should insist that your instructors actually give you proofs that are meaningful, So what follows here, I'm going to prove for you guys that in fact the continuity of the derivative for a holomorphic function, it is inevitable. And do you guys have any questions while I'm getting stuff going here?
I have a question.
Uh-oh.
Is this similar to analytic continuity?
Analytic continuation?
Yeah.
I wouldn't necessarily think of that. To me, analytic continuation is more a discussion about, well, specifically it's a discussion about you're given a function that's described by a power series, right? And then the question is, can you recenter the power series, right, such that it overlaps, it agrees on an overlap of the disk of the new center versus the old? That's an analytic continuation. It's shifting power series along some curve.
Okay.
So the only example I've really showed you of that is my evil problem 19 on the test, right? Where the take-home part. That was an example of analytic continuation. However, that one is also very nice in that there is an overarching formula there. See, there's 1 over 1 minus z. I was just looking at power series representations of the algebraic function, the rational function 1 over 1 minus z. And for a general power series, you don't have to have some kind of nice closed form rational function that you're expanding. So it's a much more complicated question given a function, a complex function defined by a power series. Can you analytically continue it? It turns out that the answer to that question is nuanced and like very complicated. There are series which have a natural boundary that you just can't extend past. Like the series come built together with this like immovable circle that you can't get past. There are other ones that you can just keep going. And I don't fully understand it.
Yeah, the reason I asked is because I was looking at the Riemann zeta hypothesis.
Ah. Are you going to give a talk on that in the to Randolph?
It's too long. Like,
It's too long?
It's too much. It's too complicated of a problem to talk about in 12 minutes. I'd rather talk about it in 3 minutes because that would be funny. Like that would make for an interesting presentation if I just was like clicking 80 slides in 3 minutes. But like, I'd rather talk about, like, if I'm gonna do it for 13 minutes, maybe I should do like another problem.
Whoa.
It's easier to explain.
Yeah. Well, You know what's fun is the Mandelbrot set and the Julia sets, that stuff. That's actually very visual and interesting, the fractal stuff. And this class should make that very easy to understand. I have covered it in previous, previous iterations of this course. There are some videos by like Numberphile, which are really, really nice on this.
Yeah, I like that channel.
Yeah. All right, so I will get to it eventually. Here we are. So I will try to go through these systematically. What did I do?
It's a rectangle. I have PTSD.
You have a problem with rectangles?
After problem 75.
Oh, a problem 75. Ah, okay.
This is a different one though.
Yeah, this one's color-coded and such. So here's the theorem, Morera's theorem. Let f of z be a continuous function on a domain U if the integral around the boundary of the rectangle is 0 for every closed rectangle contained in U with sides parallel to the coordinate axes. Then f of z is holomorphic with continuous derivative in U. So what we do is we take the integral around the rectangle and basically we're going to look at this integral this way versus that way. And I say it suffices to prove the theorem for a disk with center z0. All right, so I'll do that. So gamma d is this. Let's see here. That's the down part, I think. So like this is x0 plus iy0. This is iy0 plus x. I think that's that point right there. And then we go from that point up to here. This point is x plus iy. All right, so like the gamma d is the blue curve. And I say, to show f prime of z exists, we consider the difference. And here delta z is small enough to keep the z plus delta z inside the disk, which we're assuming f is, I believe, holomorphic in that disk. We're not assuming the continuity of the derivative, though. So that's what we have to prove. We have to prove that the derivative is existing and is continuous. I think, excuse me, we are assuming the derivative exists. We're trying to prove its continuity, to be more clear. Anyway, so I take the difference of these two guys, and so I have let's see here. I say this denotes the reversal of that. I plot it as the red path below. The blue path is the gamma of z plus delta z. Let me keep going here. All right, so let's see here. So by assumption of theorem, we're able to replace the sum of the blue and the red paths by the green path. Why is that? I'm assuming that the integral around every rectangle is 0. That's the data. that we're assuming in Morera's theorem. We assume that the integral around every, reasonably, vertically and horizontally naturally situated, right, parallel to the coordinate axes, rectangles, that integral is 0. So if this integral is 0, then I can replace the integral along that with the integral along that, because the integral all the way around has to be 0. So we can play this game where we're replacing the blue and the red paths with just the green path, because the integral around the rectangle is 0. Notice that this path, these are just reversals of one another, so that piece here cancels, and we're really just looking at the integral around the rectangle. Now, anyway, I did actually read back through this about a month ago, and I think everything's correct. So anyway, here we're integrating over dw f of z. Now the z here is that fixed upper point in the rectangle, so it doesn't have anything to do with the dw, so I can pull it out. And then if you integrate dw over a line segment, you just get the displacement, which in this case is z plus delta z minus z, namely delta z. So I get f of z dz is that integral. And so if I do come back here and I add 0 to the integrand, see I added 0, added f of z and subtracted f of z, then the integral of f of z dw is f of z delta z, like I showed up here. And this, we have the integral over the upper part, which I think is the green curve in my previous picture, of f of w minus f of z. All right. But I also have that the length of that line segment is less than twice the length of delta z. And if I set m to be the supremum of the values of the difference of the function, then the ML estimate gives me that this integral is bounded by that. So if I go back up to my star-star equation on the previous page, I can find my way to this equation right here. So as delta z goes to 0, we get what? 2m, we have 2m goes to 0? Oh, I'm dummy. I'm completely missing that, right? So I shouldn't say 2m goes to 0. I should say we have to have ml goes to 0, right? I shouldn't say 2m goes to 0. What I should say is ml goes to 0. And ml going to 0 or wait a minute. Yeah, I do have 2m goes to 0. Oh, m is this. I'm bad. Does m go to 0? Yeah, of course m goes to 0 as we have delta z going to 0, right? Because as delta z goes to 0, this becomes the difference of, two values of the function that are infinitely close. I mean, this obviously goes to 0 as delta z goes to 0. So with that said, we have that f prime. This is the difference quotient for big F, right? And the difference quotient for big F is little f. Woohoo! And I say furthermore, we assumed f of z is continuous, therefore f prime of z is continuous. Consequently, f of z is both holomorphic and possesses continuous derivative f prime of z. And then if I apply corollary 7.35 to Cauchy's generalized integral formula, I will see that f prime prime, namely f prime of z, little f prime of z exists and is continuous. So that is Morera's theorem. Just to reiterate, let me tell you what it gives us for the sake of understanding the next theorem. Morera's theorem gives us that if we can show the integral, so if we have a continuous, if f is continuous, and we have that the integral around every rectangle is 0, right? Then it follows then that f is both holomorphic and its derivative is continuous. All right? So so that's the backdrop. We're going to use this. This frames the proof of Goursat's theorem that I'm about to show you. Anyway, as I was saying, the steps in this integral, they're not especially interesting, in my opinion. They're really just, again, this sort of calculus 3 path reversal, choose the right thing to see the estimate that you need kind of thing. Like, I mean, it's an interesting argument. It's clever. It's not mine. Don't ask me where I got it. But that said, when I first saw this theorem, I had that feeling of like, whoa, whoever first came up with this is a master. I don't have that feeling as much with Morera's theorem, but this theorem, it's, the argument here is really something. This Goursat's theorem, f of z is a complex valued function on a domain D such that f is differentiable at a point, all right? And it exists at each point in the domain. Then the derivative is continuous. In other words, if it's complex differentiable at each point in the domain, it is necessarily continuously complex differentiable. In other words, you cannot help but have a continuous complex derivative, right? I know you guys, it's tempting to not hear like the distinction here. In Calculus 1, we prove that if the function is differentiable, it implies that the function's continuous, right? Differentiability of the function implies continuity of the function at a point. But what we never proved in Calculus 1, and is in fact not true, is that if the function is differentiable, the derivative itself has to be continuous. That's not the case. There are real functions which are differentiable and yet have a derivative which is itself not continuous. Like probably the most easy example of that would be like x times absolute value of x. X times absolute value of x is differentiable at 0. Its derivative is, excuse me, that's not the right one to give you. Oh, anyway, yeah, Jeff, I'm getting distracted.
If a function in the complex plane is differentiable, does that mean that it's infinitely differentiable?
Yes. That's right. There's only complex smooth functions. There's no like once complex differentiable functions. That we had last class. However, the fly in the ointment of the theorem was that we have yet to prove that complex differentiability implies that the derivative is continuous for the complex function. Like we have, if one derivative exists continuously, then so does the second and the third and the fourth and whatever, but we had to assume the continuity in that. Okay, anyway, so here, so we assume that we have a function which is everywhere complex differentiable in some domain, and what we're going to do is we're going to show that the integral around an arbitrary closed rectangle is necessarily 0. And once we do that, then we apply Morera's theorem to get continuity of the derivative. So all we have to do is prove that this data is enough to prove that the integral around an arbitrary closed rectangle in the domain is 0. That's the proof. But the proof is far from obvious. So here's what I do. We take a closed rectangle, sides parallel to the coordinate axis. We divide R into 4 identical subrectangles. And then we pick R1 to be the subrectangle for which the integral, the modulus of the integral around the boundary of the rectangle is the largest. So there's 4 subrectangles, right? So there's got to be one that's largest. Yeah? Think about it. There's just 4 choices, so pick a max of 4 things, right? You can do it. Now, and in that case, of course, the integral around the boundary of R1 is going to be greater than or equal to 1/4 of the integral around the boundary of the big rectangle. All right, because it's the max of 4 things. Or equivalently, we could say that the integral around the boundary of the big rectangle is less than or equal to 4 times the integral around the boundary of the first dividing subrectangle. And then what do? Again, so take that rectangle and divide it into 4 rectangles. All right, and then of those 4 subrectangles, one of those has the largest integral around the edge modulus of the function, right? So, and then we just rinse and repeat, and we obtain in this way a sequence of nested rectangles, R containing R1, containing R2, containing Rn, and it's a simple exercise to verify that the integral around the nth subdivided rectangle is less than or equal to 4 times the n plus 1th one. And if we recursively understand what that implies, you can prove this by induction to be careful. We have the integral around the outer rectangle is less than or equal to 4 to the n times the integral around the nth subdividing rectangle, which at first glance doesn't seem especially helpful because we're trying to show that this is 0, right? And we just got it's bounded by something that's 4 to the power n. That doesn't seem awfully encouraging, does it? Like what happens to 4 to the n as n goes to infinity? That's right, but the rectangle's getting tiny. So how does that help us?